comes the fun part of Laplace transforms, actually using them to solve something. Differential equations. We're going to redo the differential equations today that we've already been doing, but with the Laplace transform method. That's what a lot of engineers do, because not only can they then solve these basic equations we've been doing, but there's some other equations with discontinuous forcing functions and so forth that can also be solved by the same method. So this thing does everything together. Alright, so the Laplace transform method is very nice like this. It's a 1, 2, 3 method. You take the Laplace transforms of both sides of your equation in some independent variable u, your differential equation. You get an algebraic equation. You solve that for u of s, the transform of the independent variable u. Then, the inverse transform. So you turn your differential equation problem into an algebraic equation problem. Right? Transform the differential equation into an algebraic equation, solve the algebraic equation, inverse transform. We said last time, furthermore, if you start with a linear differential equation, all you have to solve here is a linear algebraic equation. So that's the easy kind, right? Interesting comments too. If you leave the initial values arbitrary, then you can get out the solution in terms of arbitrary initial conditions. So the Laplace transform is really set up for initial value problems. You give it a differential equation together with initial values, and it gives you back the unique solution for a nice differential equation that has a unique solution. But if you leave the initial conditions just as u0 is u prime 0, arbitrary numbers, it can give you the solution in terms of those, and then you can see what happens as you change those initial conditions. Alright, so here's how we can do this, take the Laplace transform of a differential equation. It comes out of this theorem. If f prime, a function of t, is piecewise continuous on every finite interval from 0 to a, right? These functions are only supposed to be defined on 0 to infinity, and so this has to be continuous piecewise. That means, remember, piecewise continuous means that you have at most a finite number of discontinuities in between which the function is always continuous. And each of those you have to have the limit from the left and right exist. So you can have jump discontinuities, removable discontinuities, those things. So f prime is piecewise continuous on 0a, and f is continuous on 0 to infinity, and of exponential order, the kind we said we could take Laplace transforms of on some interval from t0 to infinity. Then, at least for large enough values of s, remember, for the Laplace transform to exist, you could specify that it grew no faster than a m(e) to the at function. And if you take a out of that exponential function, you can find an exponential function that doesn't grow faster than, then this will work. And the Laplace transform will exist at least for s large enough. Remember, you don't have to have the Laplace transform exist for all values of s, just for s big enough. And then this method will work. So if it's less than m(e) to the at, then the Laplace transform will exist for s, real part of s greater than a, in case you have a complex case. We'll just deal with real s here. And so the Laplace transform of f prime in that case is s times the Laplace transform of f minus f of 0, the initial condition. So that's what it says. And then you can extend this. If you can take the Laplace transform derivative, why not the second derivative? Sure enough, if f double prime is piecewise continuous on every finite interval from 0 to a, and f and f prime are continuous and of exponential order on 0 to infinity, continuous on 0 to infinity, exponential order on some interval t0 to infinity, with some exponential constant little a. Then for s greater than a, the Laplace transform of the second derivative is s squared f of s, the transform of little f, minus s times f at 0, your initial value, minus f prime of 0, your initial derivative at 0. Here's the proof. Something didn't come out here. It jumped down onto a new line, that's what happened. If you take L of, this is supposed to be on the same line, f prime of t, that's what happens when you reformat your document, it fixes everything for you. The Laplace transform of the derivative is defined this way, e to the minus st times the derivative. And then, if you apply integration by parts, taking u equal e to the minus st and dv equal f prime of t dt, then v, this is uv minus integral v du. And when you evaluate this one, it's minus f of 0. When you evaluate this one, you can pull the s out because we're integrating with respect to t, treating s as a constant. We have this integral, but wait a minute, that's the Laplace transform of f of t instead of f prime of t. So what we have is minus f of 0 plus s times the Laplace transform of f. See how easy that proof is? And then you just do it twice. 2 integration by parts gets the second one. I'll leave that for you to look at. Furthermore, if you can do it again and again, you certainly can do it again and again and again, right? The nth derivative has Laplace transform, s to the n times the transform of f, minus s to the n minus 1 times the initial value, f of 0, minus s to the n minus 2, f prime of 0, and so on, all the way down to the n minus first derivative times 1, evaluated at 0. So the Laplace transform of the nth derivative requires n initial values in it. Alright, so now we can apply that by the three-step method, right? Solve the initial value problem to u dt plus 2u equals 0 with u of 0 equals 1 by the Laplace transform method. An easy, cheesy first order differential equation that you could easily solve by constant coefficients. Now let's solve it by the Laplace transform and see if we get the same answer, right? Take the transform of both sides. Transform of 0 is 0, we remember from the table, right? Laplace transform of the left, the Laplace transform of the sum is the sum of the Laplace transforms. So Laplace transform of both sides, sum of the Laplace transforms. And you pull the constant 2 out, right? You can pull constants out because the Laplace transform is an integral. And now, by the theorem we just had, the Laplace transform of the derivative is s times u of s minus u of 0, where u of s is the Laplace transform of little u. Plus, Laplace transform of little u, I'm just changing notation here, I'm writing L of u as u of s. And then L of 0 is 0. There it is. Algebra equation for u of s, right? You group the u of s terms together. They multiply s plus 2. Oh, I neglected to mention too, you can now put in the initial condition, right? U of 0 equals 1, so replace u of 0 with 1. And now you've got this algebraic equation. You group the u of s terms, they multiply s plus 2 on the left. And you group the other terms, minus 1. And now you can add one on each side, divide by s plus 2. It's linear in u of s, right? Just add this number over here and divide by this number. U of s is 1 over s plus 2. I know what function that is. It's in the table, right? That's the Laplace transform of e to the minus 2t, right? Because 1 over s minus a is the transform of e to the at. Here we subtracted negative 2. So there it is. The unique solution to this initial value problem solved by the Laplace transform. Let's try another one. Solve this initial value problem, a second order equation. Really, first order equations are not the thrust of these in sciences. Typically you get second order equations, sometimes third or fourth order equations. And once in a while first order equations too, but we really need to be able to solve these. Suppose I do this one, take the Laplace transform both sides. This time we have a second derivative, so we apply the second part of the theorem. The Laplace transform of the second derivative is s squared times u of s minus s times the initial condition minus the initial value of the derivative. U dot means the u dt. That's another notation for it. This was the theorem for the second derivative of Laplace transform. And then plus 3 times, here's the theorem for the first derivative Laplace transform is s times u of s minus u of 0. Plus twice the Laplace transform of u, all equals transform of 0 is 0. Well, we can put in the initial values because u of 0 is 1. So 1s here. U prime of 0 is 0, so we drop this one out. There's this one. This one's 0. Or no, this one's 1 again. So, yeah, so 3u of s minus 1. And then plus 2u of s equals 0. Algebra equation. And it's linear in u of s. You group all the u of s terms, you have u of s times something plus something equals 0. That always works out for a linear equation that this happens. So now you add s plus 3 to each side, divide by this stuff, and you get u of s is this. How do we solve this one now? Step 3, right, we took the Laplace transform of both sides in step 1. We solved algebraically in step 2, but step 3 is the inverse transform. Not such an easy one here, right? This isn't in our basic table. You can actually look this up in our more advanced table that's coming up, or you can get it online. There's just Google Laplace transforms, and they have lots of them there, lots of tables out there. And calculators online, Symbol Lab, not Symbol Lab, but anyway, calculators out there to do this for you. And how can we do this one though, with a table or by hand? With the table we've already done, actually we can do this, and it just takes partial fractions. This is a common thing to do when you're solving a second order differential equation. You first factor the denominator, if you have a quotient of polynomials like this, and then recognize that partial fractions will allow us to rewrite this as a difference of two quotients with the denominator first order, right? By partial fractions, this is 2 over s plus 1 minus 1 over s plus 2. So now I need the inverse transform of this, but this is easy. This is in our basic table that we used last time. All right, you're right. Inverse transform of the difference is the inverse of the difference of the inverse Laplace transforms, and I can pull the 2 out. And now I recognize this is in the table. This is the transform 1 over s minus a of e to the at, so it's e to the minus 1t. This is the transform of e to the minus 2t. So we get as our unique solution 2e to the minus t minus e to the minus 2t. All right. Well, it sounds like it's all straightforward, but actually, if the denominator here can't be factored over real numbers, it's a little more difficult. It's really awful dealing with those complex factors, so usually people only use that factoring when it factors over the real numbers. How do you know? If you have as squared plus bs plus c on the bottom, if b squared minus 4ac is at least as big as 0, then the quadratic formula gives you 2 real solutions, right? Possibly equal if b squared minus 4ac is equal to 0. And then you can factor it like we just did, and that'll work. But if b squared minus 4ac is less than 0, then it only factors with complex numbers. And rather than do that, we're going to try completing the square. And then when you do that, it's useful to have this theorem known as the first shifting theorem, since we're going to have a second shifting theorem coming up. Shifting because what is this the graph of if I graph this f versus s? Right? F of s, if you replace s by s minus a, remember it just shifts the whole graph over a units. This is what you learned in algebra. That's just to remind you, I want to show you what's called the shifting theorem. It's never pointed out in books for some reason. They just expect you to remember this, and a lot of people don't. Suppose I have the basic parabola, y equals x squared is f of x. What is the graph of y equals x minus 1 squared? That's f of x minus 1, right? I replaced x by x minus 1 in here. So if I know the graph here of y equals f of x, what does the graph of x minus 1 look like? Well, if you think about it for a second, to get the same y value out here as you did here, you have to just make x1 bigger, right? If If you put in 0 here, you square 0 and get 0. If you put in 1 here, 1 bigger, you square 0 and get 0. If you put in 2 here and get 2 squared, you have to put in 3 here to get 2 squared, and so forth. You just have to put in x1 bigger, so instead of 0, 0, you get 1, 0. Instead of 1, 1, you get 2, 1. And every point is shifted 1 unit. We call this shifting. When we replace x by x minus a number that shifts the graph over rigidly, it's still exactly the same shape, right? Hence, here we have a shifting theorem, because in the plot of the transform as a function of s, the graph is shifted over. And here's the proof of the shifting theorem. This isn't bad either. I think it's worth seeing when they're simple and illustrative like this. The Laplace transform of e to the at times a function. It's like this, right? The Laplace transform of anything is e to the minus st times whatever you're taking the Laplace transform of. Now you can combine these two exponentials by algebra as e to the minus s minus at, all times f of t. But what is this? This is the Laplace transform if you just call this s instead of s minus a, right? So if you call this Laplace transform f of z, this is the Laplace transform z, but z is just s minus a, and so this is just the Laplace transform where s minus a is the variable instead of just s. All right, now can we use that to solve this one, where you get a denominator that doesn't factor over the real numbers, because b squared minus 4ac is negative. U double prime plus 6u prime plus 10u equals 0 together with these initial conditions. U of 0 equals 0, du dt at 0 equals 1. Remember, the Laplace transform is set up ideally to deal with an initial value problem. An nth order differential equation with n initial values. It works best for these linear equations. It does work on some nonlinear equations, but not so many. So the nice thing about this is, too, we'll do almost all linear equations with the Laplace transform. They're easier. When I take the Laplace transform of the differential equation, the Laplace transform of the second derivative, remember, is s squared times the transform of u minus s u of 0 minus u prime of 0. All right, so there's the Laplace transform of the second derivative, plus 6 times the Laplace transform of the first derivative is s u of s minus u of 0, recall, plus 10 times the Laplace transform of u we call big U of s. All equals Laplace transform to the right of 0. This doesn't work just for homogeneous equations where we get 0 on the right. Don't think everyone's going to have 0 on the right. But we haven't done enough tables yet to want to do a whole lot of those examples yet, but they're coming right up. All right. Put in the initial values. For u of 0, we put 0. But for u prime, we put 1. So we got a minus 1 here. And this is 0. Here's the equation now, the algebraic equation. That was step 1. Step 2, we have to go back to algebra, prove the u of s is here, times all this stuff. Minus 1 equals 0 on the right. Add 1 on the side, divide by this. Here's the Laplace transform of the solution, so we just have to inverse it, right? Well, inverse of 1 over s squared plus 6s plus 10 doesn't factor with real numbers. We're going to avoid those terms with I in them, and instead say, let's complete the square, all right? What do we need to make a perfect square down here? S squared plus 6s plus what makes a square? Remember, you take 1/2 of this number and square it. So 1/2 of 6 is 3, square root is 9. I need 9 to make a square. I have 1 left over here. And that's what will happen in this b squared minus 4ac less than 0 case. If you complete the square, you'll have a positive number left over. So I'll get 1 over s plus 3 squared, right? S squared plus 6s plus 9 is s plus 3 squared, and then plus 1 more make 10. What's the inverse transform of this? Shifting theorem. It went to the next line again, didn't it? By the shifting theorem, we said, wait a minute, I know what this was. If it was just 1 over s squared plus 1, that would be the transform of cosine t, right? What is it when it's not 1 over s, but with s shifted? The transform of the shift function that's shifted replacing s by s minus a minus 3, right? The shift is whatever you subtract, right? If you subtract one, the parabola was moved one to the right. So the shift is minus 3. We multiply by e to the minus 3t, the inverse transform of what we would have had here, 1 over s squared plus 1. That's the shifting theorem we just wrote. Oh, but I know 1 over s squared plus 1 is the transform, of sine. 1 over s squared plus 1 is sine. Transform the sine. And so we have e to the minus 3t sine t. S over s squared plus 1 is cosine. Alright, so there is the inverse transform of this function. And the solution to this differential equation is e to the minus 3t sine t. And then finally we can solve these, we said, in terms of initial values. If I just replace u of 0 with u0 some number and du dt at 0 with u dot 0 some number. So these are the numbers that are the initial values. Right? This equation is called an initial condition. The number here is called an initial value. We take the Laplace transform of this. U double prime plus 5u prime plus 6u equals 0. We get, here's the transform of the second derivative plus 5, transform of the first derivative, plus 6 times u of s equals 0. And we replace u of 0 with u0 and u prime of 0 with u0 dot, those two numbers. Now we apply algebra to solve for the transform u of s as usual. And we get u of s times this stuff minus this stuff equals 0. So we add this over and divide by this. Here is u of s, the transform of the solution by algebra without knowing what the initial conditions are. Right? We just leave them arbitrary. Now we can go to the inverse transform of that to find what's our solution. Well, we can apply partial fractions to this one because this factors with real numbers, right? S plus 3 times s plus 2 is how that factors. Partial fraction shows that this actually factors like this. You can do this on your TI calculator, or you can do it by hand, or you can do it online on some of those calculators. Sometimes partial fractions gets tedious with arbitrary numbers up here, but you can still do it. This is how it factors in terms of these numbers, and so the inverse, this is a constant here, right? These are just numbers. The inverse transform of 1 over s plus 2 is e to the minus 2t. The inverse transform of 1 over s plus 3 is e to the minus 3t. These are the constants. The solution is u equals this number times e to the minus 2t minus this number times e to the minus 3t. And there it is, the solution in terms of initial conditions. If you, for instance, wanted to wipe out the term that decayed most slowly to make this decay faster, you just pick 3u0 plus u prime 0 in your initial conditions to be 0, and you'd have only this, ideally. In fact, it's hard to put your initial conditions so perfectly that you completely get rid of this, but the idea is you can try and design your circuit or something to get this to damp out faster if you make this as close to 0 as you can, right? About the charge or current or something to damp out. All right, there it is. Try some problems.